and I'm going to be talking to you today all about choosing areas of interest for ESA's prospect instrument for landing at the South Polar region of the Moon. And what I'm going to talk to you about tonight is on behalf of the Prospect Landing Site Working Group. So it's a big group project that we're all working on together. Okay, so just to start off with, I have a few things for you to think about as I go through the presentation this evening. The first of all is that, as Chilla introduced for us, the lunar South Polar region is of much interest and a target area for many future missions, including for ESA's prospect instruments. We're going to be landing within the South Polar region of the Moon. And when choosing a landing site or an area of interest, you need to take into account both the science requirements of the mission, but also the operational requirements as well. And these two things are really key when selecting your areas of interest. And also important is the landing site has to be suitable for all instruments on the mission. And so sometimes there have to be compromises as to where you go. And when you're having a landing site selection, this requires really high resolution data sets to be used to make sure you get the most information as possible and to then make your choice with your landing sites. So just as a little refresher for, on the lunar South Polar region, as Chilla mentioned earlier, just before the break, we have the, let's see if I can get the laser to work. Yeah, we have the South Pole itself is located on Shackleton Crater, right in the centre of this map here, and we have a Munson crater just off to the right, Douglas just to the left, and I'm going to be talking about this region in particular for areas of interest. And just for reference, this is a elevation map or a topographic map where areas in blue is high areas of elevation, so typically like big hills or mountains or plateaus, like up here, the dark blue, and then red is the kind of craters or lower areas of elevation. So what is ESA's prospect instrument? Prospect has the acronym which is for the Package, Resource Observation and In Situ Prospecting for Exploration, Commercial Exploitation and Transportation. So it's a really long word, but Prospect for short is one of the instruments that will be on the NASA Eclipse 22 mission. So this is one of these missions where commercial companies combine with NASA to put a mission together, and we're just one of the instruments that is on board this mission. So what is Prospect? Prospect has a drill that will drill beneath the surface of the lunar surface down to a depth of up to 1 metre. And what it will do is it will take these samples and will put them into the little mini ovens that make up the onboard laboratory known as ProSpar. These ovens will heat the samples up, and then when this heating process is happening, we will measure any of the gases that are given off from the samples. And what Prospect is designed to measure is gases from volatiles such as water ice from the lunar surface. And therefore we want to go to an area where we can expect water ice to be stable if it's present. So these are the requirements or the list of things that we need to take into account when choosing areas of interest for Prospect. So as I mentioned, we want it to be within the South Polar region. So the study area, or the area we're looking at, is from 84 degrees south all the way down towards the pole at 90 degrees south. We wanted to make sure we didn't land within a Artemis 3 candidate sites. These are the sites that Chilla introduced earlier, these areas of interest that NASA have identified. And we needed to make sure the landing site meets the requirements for Prospects. This was making sure that we landed in somewhere that was scientifically interesting and kind of geologically and also thermally. We wanted to go somewhere that's cold, so it's out there finding water ices in cold places. The landing site also needs to be safe, so this means landing on a nice flat surface where there's slopes of less than 10 degrees, and with minimal observable hazards, so where there's any hazards can be such as a crater or a boulder, and any hazards that are there need to be less than 5 metres in diameter, so kind of rough approximate. And the idea of looking for somewhere where a 100-metre diameter landing ellipse could fit nicely so we can land at this region. And I'm going to talk to you all mainly about tonight is the scientific kind of requirements, looking for somewhere that's scientifically interesting for Prospect. So how do we do this? How do we find areas of interest? What we do is we use data sets from remote sensing methods, so from satellites orbiting around the moon, we take lots of these images and different data sets and combine them all together. And we applied a filter, so we were basically filtering through the data sets to look for areas where there were slopes of 10 degrees or less, so a nice flat area to land on, where there was temperatures cold enough for water ice to exist, and we used thermal models to look at this. And what we were looking for was for areas where the thermal models showed there to be water ice present, to be stable if present, beneath the surface of about 0 to 20 centimetres beneath the lunar surface. And also where there was illumination and earth visibility of greater than 40%. And this is because the mission is going to be solar powered, and therefore we need to have solar illumination in order for the solar panels to pick up and in order for the mission to be successful. And also, as we mentioned earlier, we need earth visibility for communications and be able to talk to our lander, and also to get the data back as well. And what we did was we looked for any areas where there was 4 pixels, or in this case 480 meters size of an area that met these requirements just above. And anywhere where these criteria were matched, we marked a point, and these are shown by the red dots on this map over here. And for reference, the blue squares are the Artemis 3 candidate sites. So we originally had 49 points of interest, or areas where we wanted to look in a bit more detail, and we needed to narrow this down. We needed to kind of zoom on into just a few sites. And so how did we narrow this down? We started by looking at sites that then had thermal conditions between 0 and 10 centimetres beneath the surface. So this would be where we could expect there to be cold temperatures for water ice to exist. And this then gave us 18 sites. From this 18, we then down selected to 12 by looking for sites which had previously been recommended by previous studies, so looking at what others had found as areas of interest. And this then made us 12 sites of interest. And then from this 12, we narrowed it down to 4, which I'm going to talk to you about this evening. And these 4 sites we ranked, or we scored them, based on a series of questions. And these questions could be answered with a yes or no. So things like, is the site geologically interesting? If it was answered with a yes, it scored higher. And if it answered with a no, then it was scored lower. And then we added up all the scores from all the questions, and the highest scoring sites were then ranked the highest, and these are the ones, the 4 that I'm going to talk to you about this evening, were the top scoring sites. So where are these 4 sites of interest? I've given them little names to make it a little bit easier to remember and to understand what we're talking about. So the first I'm going to talk to you about is the one here. This is POI 12. This was closest to the Shackleton crater, so Shackleton is just here and just above it. This is the first site I'm going to talk to you about. I'll then talk to you about a site over here. This is, I've called it near a big crater site. This is near Cabeus crater. Then we've got one here that's on the ridge between the Gerlach and Haworth crater. That's on the ridge site. And then one on the crater rim known as on the rim of Amundsen crater, just here. But so first of all, we're going to take a little trip to this site here. So this is the closest to Shackleton crater, and this is a series of different data sets I'm going to talk you through. And this was information that we used to kind of look into more detail at this particular area. So starting on the top left here, we have an elevation map. So this is simply just showing how tall or how high things are and how shallow they are. And for reference, the red is showing areas of high elevation, such as a hill, and blue is showing lower areas of elevation. And from the red to the blue, we're seeing a difference of about 70 meters. And for reference, that's about the height of a small hill, or just a little bit smaller than the pyramid. So we're not talking big mountains yet, we're talking a very small difference. But what you can see from the top right image is that the slopes in this region are all coming up in blue. So this blue colour is showing slopes mostly between 0 to 10 degrees. So nice and flat areas, which means we would have a nice, safe landing. The bottom left here is a mosaic of photographs from the narrow angle camera. So this is simply photographs of the lunar surface. And what you can see is that the whole region has got little craters and also some slightly bigger ones where there's some darker regions. These are permanently shadowed regions that Chilla mentioned about earlier. And we've got some areas that are illuminated as well. So showing that there's a nice range in topography there. And we have a contour map here just showing the point of interest and then the region surrounding it. And so hopefully what you can see is that we're on this high point of elevation, and then there's these crater basins and areas of lower elevation just surrounding it, giving this really interesting topography to the region. And to talk about the illuminations, this is what we need for those solar panels to work on our mission. This is a map of the shadows. So this is where there's continuous shadow day after day. And we have in red shadows of up to about 30 to 40 days continuously, but then the rest of the time it's illuminated, so this is really good. And then on the right we have areas of high illumination in green, so you can see that throughout the region there's lots of green dots, so this is good. This means there's more than that 40% illumination throughout the year. So this was a really good site in terms of the illumination conditions and also thermally as well. And moving on to our next site, we have near the big crater site and conveyance over on the left hand side. That's where I'm going to next. So the same thing, I'm going to show you the same 4 data sets for each of the sites. We have on the top left here, we have an elevation map. Again, the elevation difference is not that much. We're talking about 60 metres. Again, small hill. And then on the right panel, again, we have nice flat slopes of about 0 to 10 degrees. So nice and flat, suitable for landing in. What you might notice is that there's some more red colours on these craters here. So you are getting steeper slopes. So this is something you need to be aware of if you were to land here. These craters may cause a little bit of a hazard. But for instance, if you were to land in this region, the slopes are much flatter. And you can see those craters in the narrow angle camera mosaic in the surface images. You can see that there's lots of craters distributed in this region, which would potentially be a hazard to your lander and to your mission, but there's other areas where there's much less, which would be more suitable. And the contour map in the bottom right here, you can see that there's these steeper slopes and the contours of that more squished up tightly together, and we're on this kind of ridge or plateau, so it's a suitable area to go to. And then again, the illumination conditions, you can see on the left it's all red, meaning there's only up to about 35, 40 days where there's continuous shadow, and on the right you can see it's mostly green, so this is really good. It means there's good illumination conditions, and so it would be suitable for a successful mission. And so our next trip we're going to go to is to the Golilocks Ridge, here just between the Golilocks and Hayward Crater. And again, those 4 data sets for you. We have high areas of elevation in the red again, and you can see there's a slight decrease in the elevation going across the map here, and this decrease is about 100 metres of elevation, so a little bit bigger, about the height of the pyramids for reference. And the slopes, here we have a bit more going on. The slopes along the ridge itself are nice and flat between that 0 to 10 degrees, so this is good. But what we need to be aware of is that this region down here where it's all red, these are much steeper slopes and therefore wouldn't be suitable to land in this mission. So that would be land in this area, so that would be something we need to take into account. And you can see that also in the image here. You can see that this region is just in total darkness, as that would not be good for if we were to land there. You would not be able to then do your mission operations. So again, something to bear in mind. And you can see that in here on the contour map, you can see that we're in an area that's a high elevation, but either side we've got really steep contours, and you've got these craters over here, so the illumination conditions are a bit more complicated. And you can see that in the maps here as well. So we have short shadows for most of the region on the kind of the left-hand side of the image, but then on the right you can see that there's more yellows and some greens creeping in as well, so there's less good illumination conditions. And you can see that in the right panel you get this big red area showing that there's not as much illumination as we had in the previous 2 sites that I showed you, but the left-hand side is nice and green, so this side would still be suitable. So you'd have to be a bit more careful as to where you targeted within this region if you were to land here. So our next site we're going to is to Amundsen crater. This is a site that's on the crater rim itself. So some interesting conditions there. We have the elevation map. Again, you have this decrease in elevation going from the red down to the blue as we go along the crater rim. Again, about 100 metres, so still only a small hill. We're not quite making it to big mountains yet. And you can see the slopes of that crater rim, nice and blue and a bit of yellow, creeping in along the rim itself, but then down into the crater wall. So if you think we're going into the crater just to the right here, it's a lot more steeper, a lot more yellows, a lot more oranges and reds, getting up to about 30 degrees slope. So again, it'd be something you need to think about if you were to land on a crater rim. How would that look like if you were to accidentally be a little bit off your target and you were ending up on the crater wall, how much of an issue would that be? What we can see from the surface images though is there's really good illumination. You can see that this area is really nice and bright. You can see there's a little crater that's right in the centre of this region of interest, and lots of smaller little craters as well, but not too many big hazards, so this is really good in terms of landing there. And you can see in the topography we have this area that's located on the crater rim, and then you can see the steep crater walls where there's all these lots of contour lines all joined together, showing the steepness of the crater wall as you go down into the crater itself. And the illumination conditions, again we've got good illumination, not too long shadow periods. We're looking at about 10 to 35 days of continuous shadow. And then the illumination, again we're nice and green on this side, red on the left hand side, so this is the area that would be better to land in from the illumination point of view. And so they are the tour of our 4 sites of interest. And what we wanted to do is we wanted to pick the 2 best ones. We wanted to propose an area that we thought is the best area to go to for prospect, purely based on the scientific requirements, and then a kind of reserve area. So the POI 12, the closest to Shackleton crater site, this was picked as our proposed site of interest. And this is because of the illumination conditions, the thermal conditions being better here, and also the surrounding topography, meaning that there's nice cold temperatures and lots of fairly shallow regions within the surrounding area. And it's also in an area that's of geological interest as well, so this is really good scientifically as a site. We then chose the near a big crater, so near Cabeus crater, as our reserve site. And this is because it, again, is in an area of geological interest, so it's an area that's interesting to sample. And again, the illumination conditions here are much better than the 2 other sites. So this is why we proposed these 2 sites as our top ones. And so we then did some crater mapping, so mapping out all those hazards that are within the regions of interest. And you can see that any craters are marked in yellow, and these are where there's craters of 5 metres or more in radius. And then the areas in blue are areas where you can potentially land with a 100-metre landing ellipse. And so there are several areas across both of the regions. So our near to Shackleton crater is on the left, and this is the one that's near to Cabeus crater on the right. So hopefully you can see that both these 2 areas are scientifically interesting for prospect, and potentially would be good landing sites for the future mission, or for other future missions as well. So just to leave you with some kind of final thoughts or things you might want to think about over the next few days with the upcoming mission as well from China, is, as both me and Chin have talked about, there's many space agencies and also commercial companies targeting the moon, and in particular the South Polar region, within the next few years. So I'm asking you guys the question, what will the surface look like in 5 years or 10 years with regard to the number of instruments landing there, landers, rovers, astronauts, astronaut bases, and so how will this South Polar region kind of change and become this kind of crowded space with so many missions targeting the same area? So what will that look like, and kind of sharing the space we have there? And then how will the next 5 to 10 years shape the future missions? So shape the kind of future settlements on the moon, this idea of using the moon as a launch pad to Mars and to other planets and beyond. And with that, I will leave it there and take any questions. Thank you.
Thank you, Sarah. Any questions?
Yeah, so you generated these reports where it would be good to land, but then how do you do this? Because the spacecraft is from NASA and the instruments from ESA, and there's many other instruments. How does this get dealt out where it actually lands eventually?
Yeah, that's a really good point. So and this is what's just happened for our mission, this might be different for future missions. As Prospect had a lot of requirements and we have to go somewhere that's scientifically interesting, scientifically cold, we were actually involved in the landing site selection process. So all the different instruments that are on board that mission group together, and we have virtual meetings, etc. And you then have this selection process, making sure that you take into account not just our requirements as Prospect, but also the requirements of the other missions, the other instruments, and also the mission operations requirements as well. So you basically lots of group meetings, lots of discussions, and then narrowing it down to a line of sight.
Thank you for the talk. Is there something else going on in the North Pole? There are similar missions, or number of missions going in the North Pole?
There's not quite the same amount as there is targeting the South Pole, but there is still some interest in the North Pole, and there's still a lot of research going on as well, looking at the North Pole as well as the South. So I think this is also an area that maybe some of the missions that don't need to exactly go to the South Pole, maybe that's an area they can go to instead.
And why the focus on the South?
Just because of the more kind of expected resources there in terms of water ice. Also, we talked about Cabeus crater. This is an area where there was a mission that impacted into the crater, and we had this water ice found. So more the interest from those previous measurements and taken over the few years, and then people from that wanting to go to the similar area, and also geologically interesting as well.
So I have two questions, and actually they build on the last two questions as well. So I guess following on from that one, obviously it seems there's water ice at the South Pole. I wondered if there is water ice at the North Pole, and if not, why not? That's the first question.
Yeah, really good point. So just as a kind of I guess a broad mark is that we don't actually know. No one's actually taken a sample as of yet, and that's what a lot of these missions going forward would hope to do. So this is all based on thermal modelling, and just from this one measurement we have from this impact crater. So it kind of looks like there might be some more at the South Pole, but there's still expected to be water ice in the North Pole as well, so similar conditions.
And there's a second question, if I may. Just, following on the first one, and where you said there's a kind of primary landing site that you would hope for prospects and a backup site. What would make you choose the backup? What would happen? What would maybe go wrong in the operations or something that would make you choose the backup rather than the primary landing site?
There's a number of things. So there can be things like mission requirements, such as we need to have operation days of 8 days or more, or we need to have so many mission windows. Where a mission window is when it's the time when you can potentially launch and have a successful operation. That would be a mission window, and then there'll be another one later in the year if you were to have, say, 2 months. That could be a reason, because then a particular site that's chosen scientifically might not then meet those operational requirements. That'll be one reason for it. Also, if another instrument on board your mission had a different requirement, say for instance they needed to be pointing a certain direction if they were a camera, or if they had a requirement they needed to go to an area of particular geological terrain, and you might need to go to somewhere that's slightly different to this. They would be the two kind of main things that would drive you to move somewhere else. But sometimes, yeah, it might be that something that's scientifically really good for one instrument doesn't quite fit the other, so they have to find like a middle ground.
Compromise.
Yeah, exactly, a compromise.
Yeah, thanks for your talk. You mentioned something about not being able to make the precise spots always, but how much power do you have over like correcting if something goes wrong, or like during landing as it landed, like can it move?
This purely depends on the lander. So a lander is purely just something static that once it hits the surface it stays in position, whereas a rover is something that they can move about. Some landers or spacecraft, they have like a radar system, so they can basically, as it's coming in, I think of it, if the ground in this instance is the lunar surface, as it's coming in to hit the surface of the moon, it can take like a scan of the area and can then detect if there's hazards, such as those craters or boulders, within the area that it's currently like targeting. It can then reshift. So some missions in the past have had that set up. We currently don't know what the lander is going to be or who's providing it, but each kind of commercial company or space agency will have their own technology to do that shifting. Typically it's with a radar scan or LiDAR scan.
Final question?
From what I understood, the pixel resolution you chose was like 120 meters per pixel. All the data you showed us now seem to be much higher resolution, so how come you only chose 120 meters?
Yes, so the different data sets have different resolutions, so sometimes you have to play about a bit. So the thermal models we had when we did this analysis was at 120 meters resolution. but the slope maps were down to 1 meter resolution. So sometimes when you correlate those all together, then you have to take into account the worst resolution of the thermal model. But yeah, this is this idea of you have to work with the best you've got. Sometimes you can produce higher resolution stuff, so the elevation models of the 5 meter and 1 meter, those you can produce relatively easy with. The thermal models is a bit more complicated to get a high resolution model. And it's just kind of using the best data sets available.
Thank you.
Okay, cool. Let's thank Sarah again.